last time looked like this. Is there anyone who needs the notes from last class? All right, sounds good. I think we all have the notes. All right. So we started our section on related rates, which was essentially any word problem involving like finding the derivatives using implicit differentiation. And we said that this technique was very good when it was really easy to find the derivative of one thing, but we wanted to find the derivative of something that was related to it. Okay, now I had this strategy to find the answer to these questions. And I'm going to go through maybe the first one to see how we solve this. Okay. Step one, I told you to draw a diagram, right? So make sure that you draw a nice picture that shows everything in the question. Step two was, at this point, we need to figure out, okay, what do our variables actually mean? So if I have V, what does that mean? If I have an R, what does that mean? Okay. Step three was, I want to very clearly organize what the question is giving me. So what variables am I given in terms of the derivative with respect to time? And I also want to figure out what I want to find in terms of derivatives. So what derivative am I looking for? Once I'm done doing that, step four is to find an equation that relates all the variables that I'm looking at. Usually either the question gives it to us or we're going to have to use the geometry of the question to figure out an equation, which we'll figure out today. Step five is to take the derivative with respect to t using implicit differentiation, which we did on our quiz, right? And then step six was to plug in everything at the end. So if it gives us dv dt, like one of the derivatives, we can plug that in. And if I'm looking at the derivative at a certain point, like if it asks us to find the derivative when the radius is something, I would also plug in that number as well. The units work the same way as the numbers do. So your unit should work out just as if it were like a variable or something like that. Okay. So we did two examples. We did air being pumped into a spherical balloon. We also did the edge length of a cube increasing. And the funny thing about these were they were very simple. They gave us the equation and we didn't have to think about the direction that anything was moving. Okay. In example three, we're going to have to think about how things or where things are going instead of just plugging in numbers. Okay. So let's take a look at example number three now. Example three, we have a spherical snowball and it's melting in this way that it stays a sphere, by the way. Probably not in real life. Snowballs don't do that, but let's pretend it does. And let's just say that the surface area of the sphere is decreasing at a rate of 1 centimeter squared per minute. Okay, so the surface area is all the area outside the sphere. Okay. We want to find the rate at which the radius decreases when the diameter is 10 centimeters. Okay, now it gives us a little equation for surface area there. Let's go through the steps and see how this one is a little bit different than the examples we've done before. Okay, so step one is drawing our diagram. Okay, now I'm not very good at drawing circles, so I'm going to use my iPad to help me draw this. Let's see if that works. Wow, look at that, perfect sphere. Okay, a sphere has a little diameter and radius that we can kind of draw in here. So the radius of my snowball can be found by taking the center point of my snowball and drawing a line to any point on the outside, maybe this point here. Okay, and I know that the surface area is decreasing because the snowball is melting at a rate of 1 centimeter squared per minute. Okay. I think that's pretty much all I can label on my diagram. So let's go to step two. Step two says I need to figure out what my variables mean. Now, because the formula kind of gave it to me already, looks like surface area is going to be S, right? So let's just write that down. And R is the radius, right? Pretty self-explanatory variables there. Okay, let's go to step three. here's where things get a little bit more interesting. We have to think a little bit harder for this. Okay, step 3, we have to figure out what we're given, and we also have to figure out what we want to find. So what change or what derivative is the question giving us in this example?
Giving us the rate of surface area decreasing by 1 centimeter squared over.
Perfect. And what derivative would that be? D.
ds over dx.
Not dx, but dt. But okay, I guess x would work too. But let's do dt. Okay. And you said it was decreasing at a rate of 1 centimeter squared per minute. Okay. Yeah, I was just about to ask, right? Why is it negative?
Because it says it's decreasing, which means it's less
Good. Yeah, when something's decreasing, it means that the derivative is negative. So in this question, we're not just thinking about putting numbers to different derivatives. We actually have to think about the direction in which we're changing. Are we decreasing? Are we increasing? In this case, since we're decreasing, there's actually going to be a negative next to my ds dt. Okay. Let's figure out what we want to find. Looking at our question, it says we want to find the rate at which the radius decreases, which means I want to find dr dt, right? And it's asking us to specifically find this rate when the diameter is 10. So when the diameter is 10 centimeters. Okay. Now, I don't actually have a symbol for diameter. So what does the diameter being 10 centimeters actually mean? What does that mean about the radius? It's 5 centimeters, right? Because the diameter is just twice the radius. Okay. I think that's pretty much all my equation is giving me. So why don't we move on to step number 4? Step number 4. Step number 4 tells us we need to find an equation that relates our variables. Well, the question kind of gave it to us. So why don't we just write down s equals 4 pi r squared. Okay. Moving on to step number 5. We're asked to actually take the derivative of our equation. Let's do that. So what's the derivative of s with respect to t? Perfect, ds over dt. On the right-hand side, we have a 4 pi, which is just a constant. So I guess I can put that on the outside. What's the derivative of r squared? Times?
dr dt.
Perfect. Remember, we're doing implicit differentiation, and we're taking this with respect to t. So anything that we take the derivative of, we also have to put on dr dt or ds dt next to it. Okay. So cleaning this up, it looks like we have ds over dt equals 8 pi dr dt. Okay. So we want to find dr dt. So maybe I should divide by 8 pi to get dr dt by itself, right? This is what I want. So I'm just going to divide to get 1 over 8 pi ds over dt equals dr dt. And it looks like I got what I wanted to find by itself. All right, step 6.
Got the
This
R.
is my plugging in stage. So it means that I have to plug in what I'm given, ds dt, and I also should plug in r equals 5. Okay, so I'm going to go ahead and do that. I have 1 over 8 pi. I have ds dt, which is -1 centimeters squared per minute. I actually can't plug in r equals 5. Does that matter? So I actually didn't. Yeah, I didn't actually use 5 here, but because my derivative doesn't have an r in it, then I guess I don't actually need to plug it in.
Why'd you leave the R?
Oh, was there a question?
Yeah, I have a question.
Yeah, what is your question?
For the step where it's dsdt equals 4 pi times 2r drdt, why'd you leave the r?
Oh. Okay, darn it. Thank you so much, Liam. Okay,
Michael,
I forgot an R, didn't I? There should be an R next to the 8 pi. There should be an R next to the 8 pi here. And then there should be an R next to the 8 pi there and an R next to there. Thank you so much. Okay, so I guess the R really does matter, doesn't it? Darn it. Okay. I thought I would make it through one class without making a mistake, but darn it. Okay. Thank you so much. All right, so I guess we do have to plug in R. Darn it. We have 8 pi and R is 5 centimeters. Guess it does matter here, right? All right. So that's my dr dt. All right. Any questions so far? I know it kind of just confused you a little bit by making a mistake, but hopefully you can look past that. All right, looks like we're left with -1/40 pi. What's my unit going to be?
Centimeters per minute.
Good, right? Because one of the centimeters squared is going to go away, and I can cross out one of the centimeters. So I'm left with centimeters per minute. Okay, so I know that my derivative is -1/40 pi centimeters per minute, which means the rate of decrease, which is what the question was asking for, is just the positive version, right? So how fast it's decreasing is going to be 1/40 pi centimeters per minute. Okay. Any questions on any of these steps that I went through?
How did the centimeters, how did it become from squared to not squared? Where is it?
Because there's a centimeters on the bottom, and then there's a centimeter square on top, so one of the centimeters crosses out. Good question there. Any other questions? Sounds good. All right, so I would make you do one, but I didn't put a very similar example on here. So we're actually going to go to example 4, and I'm going to go through that with you as well. And if we have time, you can work through example 5. All right. So flipping our page over, we have a different type of question now. As you look at this question, there is no equation given to us, which is kind of scary, but it's okay. We'll work through this. It says that we have a ladder. It's 10 feet long and it rests against this vertical wall. Okay. Let's say that the bottom of my ladder is sliding away from the wall at a rate of 4 feet per second. I want to know how fast the top of the ladder is sliding down the wall when the ladder is 6 feet from the wall. Okay. Now that was a lot of information. Let's just draw a picture and see what's actually going on here. Okay. So step 1. Oh, I think I see where you're going. I wrote step 3 instead of step 1. All right, so I'm gonna draw, first let me draw my wall and maybe the floor, okay? So we got a wall and the floor, okay? If a ladder is resting against the wall, then I guess my ladder, I'm gonna draw it in green, looks like this. Let me make a straight line here. Okay, so that's my ladder, okay? Now I already know that my ladder is 10 feet long, so let me just label that. So 10 foot long ladder. Okay. Now I know that the bottom of this ladder is sliding away from the wall at a rate of 4 feet per second. So this point here is going away from the wall at 4 feet per second. Okay. I want to know how fast the top of the ladder is sliding down. So how fast is that going? Okay. Now I think that's pretty much all the information I can put in this diagram. Let's come up with some variables. Okay. So what can I use for my variables, or what do you think I can label in this graph, David?
The right angle.
The right angle. Okay, I can label that. That'd be good. What about in terms of variables? Like what things are changing here?
The height.
The height, okay. So maybe I can label the height of the ladder, okay. And maybe, you know what? I wrote this in my notes weird, but maybe I'll just label H, okay. So H would be the height of the ladder, which in other words is the distance from the top of the ladder to the floor, right? So the distance or the height, the distance from the top of the ladder to the floor. And I'm writing it this way because it might be useful when we think about the direction that things are going, if I say it like that instead of just saying the height. Okay. Now, what else can I label? Oh, yeah.
9
Okay, we're not gonna include gravity in this one, but that's a nice observation. So we're not including gravity here.
If gravity's not doing anything, then how's it falling?
Well, you could also include like friction and all that stuff too, but let's ignore that.
That's another thing.
Yeah, we're not in physics class. All right, what else can I label on this diagram?
6 feet.
Yeah, the
What do you
distance.
wanna find?
Yeah, the distance between the bottom and the wall, right? What do you want to label that?
X or what?
Yeah, X. I guess width would work too. Since we did H, let's just do W. That works. Okay, so W is going to be the distance from the bottom of the ladder to the wall. Okay, I guess height and width would also work here, but I do want to write it in terms of this so we can see the direction that things are going. I think it might be easier to think of it in terms of distance. Okay, I think that's pretty much all we can say here. Let's go to step number 3. Okay, so step 3, we have to figure out what we're given and what we want to find. Let's start with what we're given here. Based on my diagram, it seems like we're given how fast the width is changing, right? So I know dw over dt, and I know it's going to be 4 feet per second. Is my width increasing or is it decreasing? It's increasing, right? The distance from the bottom of the ladder and the wall is actually getting bigger as the ladder is sliding to the right, okay? And I don't know why, but it's easier for me to think of it as distance when I think about positive or negative instead of thinking about the width. So this is actually +4. Okay, let's figure out what we want to find. Okay, we want to find how fast the top of the ladder is going down. So we want to find dH/dt, right? And very specifically, we want to find dH/dt when the bottom of the ladder is 6 feet from the wall. So when W is 6 feet, okay? What do we expect dH/dt to be? Do you think it's going to be a positive value or a negative value? It's going to be negative, right? Because if it's sliding down, the distance from the top and the floor is actually getting smaller, right? So let me just say expect to be negative. Okay, let's go on to step number 4. So step 4 is going to actually cause us a little bit more thinking than it normally does, because this time we actually have to come up with an equation. What equation do you think I can come up with here? Sam?
Well, first you need to use the Pythagorean theorem to find H. Plug that in.
Okay, so, oh, you mean to find H here?
Yes.
Yeah, I'm actually going to say that to the end, but nice observation there. But we can do it now if you wanted to.
That's usually what I do first.
You know what, let's just do that first then. Why don't we do that? So Sam was like, okay, it's asking us to find the width at 6 feet, but we don't actually know the height at 6 feet. And maybe we want to know what happens at 6 feet, okay? How would I find the height when the width is 6 feet tall? Pythagorean theorem, right? This is a right triangle, which means that if I plug it into the Pythagorean theorem, it'd say that the two legs squared, w squared plus h squared, equals, well, the hypotenuse squared, 10 squared. Okay. Plugging in w equals 6 feet gives us, well, you can use units here, but I'm pretty sure we know that the height is going to be in feet. So let's just plug it in without using our units here. 6 squared plus h squared equals 10 squared. 6 squared is 36. And 10 squared is 100. So I think that gives us h squared equals 64. And the square root of 64 is 8.